our real first stoichiometry problem in AP Chemistry. So calculate the mass of oxygen that will react completely with 96.1 grams of propane. Predict the mass of carbon dioxide and water that will be produced from this chemical reaction. So if you notice, they didn't give us any molecular formulas in this problem. We're going to have to supply those on our own. So the reactants are propane and oxygen. The products are carbon dioxide and water. And you're not going to be asked to know what the molecular formula for propane is, but you will be expected to know what oxygen, carbon dioxide, and water are. So propane, I'll go ahead and write down. And you want to give yourself a decent amount of space in stoichiometry problems so you can write above, below, and to the side when you're balancing the chemical equations. But propane is C3H8. Oxygen, remember oxygen's a diatomic, so O2. Carbon dioxide, CO2, and water, H2O. All right, the first step in any stoichiometry problem is balance the chemical equation. And all I ever do is list them down in the middle like this, and then just do the thing we always do. So there are 3 carbons on the left, 1 on the right. There are 8 hydrogens on the left, 2 on the right. We've got 2 oxygens and 3 on the right. So none of this is balanced. I like to start with the easiest one first, which they're both pretty easy. We'll do carbon first. So put a 3 here. This becomes a 3. Oxygen becomes 7, right? 3 times 2 here, 3 times this 2 is 6, plus the 1 oxygen over here is 7. Let's balance hydrogen now. So we'll put a 4 here. This becomes 8. Oxygen goes from being 7, now it's, let's see, 3 times 2 is 6, plus 4, this is 10. Okay, and oxygen, to balance that out, I just need to put a 5 right there. So our chemical equation is balanced now, and we can actually start the stoichiometry. So there's 2 approaches you can do at this point, and this is kind of a little logistics thing. You can erase where you balance so that you have room under it, or you can rewrite the fully balanced chemical equation below. It's up to you. Erasing on the computer is pretty easy and it doesn't make a mess, so I'll erase. But if you like to keep your paper neat, you can always write the balanced chemical equation below all of the kind of the work we did to get through balancing the chemical equation. But it is important in this class, and really in any science or math class after this, that you keep your work neat. Okay? People need to be able to understand what you're writing. So we got our balanced chemical equation. I like to put the amount of grams above, or really like what I'm given in the problem, I like to put above. Okay, unless it's moles. I always have a special place for moles right below each chemical. So we've been given 96.1 grams of this. Okay. We want to know the mass of oxygen, so we want to know how many grams of oxygen are required to react all of that. And we want to know how many grams of this we're going to make and how many grams of this we're going to make. All right, so step 2 in any stoichiometry problem is try to get everything in moles that you can. So obviously the only thing we can get into moles is this thing right now. So how many moles is 96.1 grams? You need to be thinking to yourself, what tool do I need to use to go from grams to moles? And the answer is the molecular weight. You need to know the molecular weight of propane. You know the molecular formula, so you know the molecular weight. It's going to be 3 carbons, 8 hydrogens, right? So it would be 12.01 times 3, right? 3 carbons, and 1.01 times 8. You'll add those 2 together. If you don't have those memorized, which you shouldn't, okay, but if you do, great for you, just go to the periodic table. I happen to have it memorized because I've been doing this a while, but 12.01 times 3 plus the hydrogens, there's 8 of them, 8.08. That gives us the molar mass. So the molar mass for this thing is 44.11 grams per mole. You can write that down below the moles if you want. 44.11 grams per mole. Sorry, I kind of scrolled on me there. Okay, and let's double check. Yep, that's what it is. So let's convert our grams into moles. So down here is where I like to do all of this work. So we've got 96.1 grams of propane, and it is helpful to write down what you're talking about, because when these problems get more complex, if you don't write down what you're talking about, you'll often forget what you were referring to. Okay, and we want to convert this to moles, so we want moles. Right, grams is what we've got, so that goes on the bottom. Okay, I'm dividing by the molecular weight, so grams are going to cancel, and we're going to get number of moles. So 96.1 divided by 44.11. We get 2.18 moles. 2.18. That's a decimal point there. It's hard to see. But you're going to write that right below. 2.18 moles. Okay. So now we want to know ultimately what's the mass of oxygen required for this thing. We can't do that directly. We have to go through moles. Moles is the middleman of chemistry. So we've got 2.18 moles here, and we have to use a concept called the mole-to-mole ratio. It's not going to be 2.18 right here, okay? Because for every one of these, 5 of these react with it. So we need to use the mole-to-mole ratio. So I'm going to take this 2.18 moles, and let me erase here. This is a good point to make, why you want to write what you're talking about next to the quantity. So 2.18 moles of, this is propane. Okay. We want to know how many moles of oxygen. So for every 1 mole of propane, how many moles of oxygen react with it? Well, for every 1, we've got 5 based off of that chemical equation. So this is the mole-to-mole ratio of oxygen, right? So we're going to do 2.18 times 5, right? Divided by 1, but it doesn't really matter. Moles of propane cancel, and we're left with moles of oxygen. So 2.18 times 5, 10.9 moles. Kind of running out of space over here on my pad, so I'll write it down here. 10.9 moles. Let me erase that and put it somewhere a little bit better. Didn't realize I was running out of room on my writing pad here. So we'll put it over here on the left. Okay. 10.9 moles of O2. Let me double check here. Yeah, that's right. So put that back up here. 10.9. So if I want to know the mass of the oxygen, I'm going to just go from moles back to grams, right? So the molar mass of O2, remember each O is 16, so O2 would be 32. So we've got 10.9 moles of O2. Okay, I want grams. Moles goes on bottom, grams goes on top, and it's 32 grams per mole. Mole is going to cancel. So we're going to do 10.9 times 32. So 348.8 grams of oxygen are required to react with our 98 or 96.1 grams of propane. So 348.8. Okay, for carbon dioxide, it's the same exact thing. So we're not dealing with a limiting reactant here, so there's no choices really to be made on which one of these I use. If we were dealing with a limiting reactant, you choose the limiting reactant and use that one to predict how many moles of this one will be made. But we don't have a limiting reactant here. The way you know you're dealing with a limiting reactant is if I give you quantities for both reactants. So if I gave you some amount of oxygen and some amount of propane, you'd be dealing with a limiting reactant. But because I didn't, we're just asking how much oxygen is required and then how much carbon dioxide can be made. We can use either one. Let's go ahead and use the propane to be consistent here. So for every one, right, there's a 1 right here. For every 1 propane, we get 3 carbon dioxide. So we're going to take 2.18 and multiply it by 3 here. We're just using the mole to mole ratio. So that would be 6.54. And then the same thing here with water. We're going to do 2.18 times 4. Okay, 8.72 moles. 7. All right, and now to get grams of both, we just have to multiply moles by the molar mass. Okay, so if I take my 6.54 moles of carbon dioxide, 4 moles of carbon dioxide, I need to multiply it by carbon dioxide's molar mass. So moles goes on bottom because that's what I've got. I want grams. The number next to grams is 44.01, right? Because carbon is 12, O2 is 32. Well, really carbon is 12.01. So 12 plus 32 is 44.01. All right, multiply these two together. $287.8 grams. And that's carbon dioxide. Okay, for H2O, we had 8.72 moles. So of H2O times its atomic weight, which is 18.02. Okay, if you're wondering where I'm getting these numbers from, I'm just taking the numbers from the periodic table and adding them together. I just have them memorized, but if you need to, just look them up on the periodic table. In fact, most of you need to do that. I shouldn't say if you need to. You need to make sure that you remember the atomic mass of most elements. I assume most of us know hydrogen's 1.01, but regardless, go ahead and check yourself with the periodic table. Make sure you're doing it right. There's nothing wrong with that. 8.72 moles times 18.02 grams per mole. Okay, 157. Let's see, 157.13 grams of H2O. Okay, and that's stoichiometry in its most basic form. Later in the class, I might ask you how many milliliters of H2O were formed, how many milliliters of carbon dioxide were formed, and we'll use something called the ideal gas law to do that problem. All right, I'll see you in the next video.